Welcome back, everyone, to the deep dive. This time, we're going to be doing a deep dive into the world of polymers. They're everywhere.
Yeah.
You think about like the clothes you wear, the phone you're holding.
Right.
It's incredible. And we've got a ton of research articles and some fascinating notes we took from our own deep dives into this topic.
Yeah.
And don't forget that we've got a link to a fantastic material science website in the podcast details if you want to explore even further.
So polymers, they're basically giant molecules built up from these repeating units
Okay.
called monomers. So think of it like building a Lego tower
Oh, okay.
where each brick is a monomer.
So you're saying that something as simple as a Lego tower is basically a model for these really complex materials.
Exactly. And just like you can build all sorts of different structures with your Legos, the way these monomers link up determines the type of polymer and its properties. I mean, we're talking about a huge world of materials here, from natural polymers like the proteins in our bodies to synthetic polymers like plastics and rubbers.
Wow. Okay. So we've got natural polymers that are essential for life itself.
Right.
And then we've got these synthetic polymers that we've engineered for all kinds of purposes. So where do we even start unpacking all of this?
Well, let's start with the natural polymers since they're the basis for, so much of what we see in the world. Proteins, for example.
Okay.
They're chains of amino acids, and they're responsible for, everything from the structure of our hair and muscles to the enzymes that help us digest food.
So like that steak I had for dinner last night.
Yeah,
That's just a bunch of polymer chains all tangled up.
pretty much. And then there's DNA and RNA,
Oh, wow.
these molecules that carry our genetic information. They're also polymers, made up of chains of nucleotides.
Wow. So we're really talking about like the building blocks of life here.
Exactly.
These are really essential.
Yeah, and let's not forget polysaccharides like cellulose, which gives plants their structure,
Okay.
and glycogen, which our bodies use to store energy.
So polymers are really everywhere,
Everywhere.
both in us and in everything around us.
Right.
But let's shift gears for a second and talk about these synthetic polymers.
Okay.
You mentioned plastics and synthetic rubbers. Those are everywhere in our daily lives.
Oh, absolutely. Think about the polyethylene in grocery bags, the polystyrene in takeout containers, the synthetic fibers like nylon and polyester
Yeah.
that make up our clothing.
Right.
These synthetic polymers have really revolutionized the way we live.
Okay, so how do we go from these tiny little monomers to these amazing materials that we use every day? What's the process behind creating polymers?
It's all about the process of polymerization.
Okay.
And there are two main ways that polymers are formed: addition polymerization and condensation polymerization.
I'm all ears. Break it down for me.
So imagine you're stringing beads onto a necklace. That's kind of like addition polymerization. The monomers just keep adding onto the chain without any byproducts. Condensation polymerization, on the other hand, is a bit like building a brick wall. You add each brick, you need some mortar to hold them together, and in this case, the mortar is a small molecule, often water, that gets released during the process.
So addition is like this simple chain,
Yeah.
and condensation is a little bit more complex. There's some leftovers.
Right.
I'm starting to get the picture here, but what about the properties of these polymers?
Right.
Like, how do we go from a simple chain of monomers to something that's really strong or flexible or even heat resistant?
That's where things get really interesting. The properties of a polymer are determined by a number of factors, including molecular weight, crystallinity, and thermal behavior.
Okay, I think we need to break those down one by one. What's molecular weight all about?
So simply put, molecular weight refers to how long the polymer chain is.
Okay.
Think of it like this. A short chain might be like a piece of thread, and a really long chain would be like a rope. The longer the chain, the higher the molecular weight. And generally speaking, the stronger and more heat-resistant the material will be.
So it's all about the entanglement of these really long chains, creating this more durable structure.
Exactly. Now, let's move on to crystallinity.
Okay.
So this describes how ordered the polymer chains are within the material.
Okay.
Imagine a box of neatly stacked pencils.
Uh,
That's a highly crystalline structure. But if you just toss those pencils in randomly, that's amorphous or non-crystalline.
so crystalline polymers, they're like these perfectly stacked pencils, nice and ordered.
Right.
And then amorphous polymers are more jumbled up.
Exact.
Got it.
Yeah.
So how does this affect the material's properties?
Crystallinity affects things like density, transparency, and even melting point. Generally, crystalline polymers are denser, more opaque, and have higher melting points than amorphous polymers.
It's amazing how something as simple as like the arrangement of these chains can have such a big impact on how the material actually behaves.
Right.
So what about thermal behavior? You
Okay.
mentioned that a little bit earlier.
Right. So some polymers are thermoplastic, which means they soften when they're heated,
Right.
and they can be molded into different shapes. Think about like those plastic water bottles you can easily crush. That's because they're made from a thermoplastic polymer.
Okay, so thermoplastics are kind of like Play-Doh. You can reshape them with a little bit of heat.
Exactly.
What's the other type?
The other type is thermosetting polymers. These harden permanently after being heated, and they can't be remolded.
Oh, okay.
It's kind of like baking a cake.
Mm.
Once it's baked, you can't really reshape it without breaking it.
So thermosets are like that hardened cake.
Exactly.
Once they're set, they're set.
Right. And this distinction is really important because it determines how a polymer can be processed and used in different applications.
This is fascinating.
Mm-hmm.
But, whenever I hear the word polymer, I immediately think of plastic. Are all polymers plastics?
That's a really common misconception. While plastics are a type of polymer, they're not the only kind.
Okay.
We already talked about natural polymers, like proteins and DNA,
Right.
which are definitely not plastics.
Right. So there's a whole world of polymers out there beyond like the plastic containers in our kitchen.
Absolutely. And there are even some synthetic polymers that aren't plastics, like Kevlar, which is used in bulletproof vests, and silicone, which is used in everything from lubricants to medical devices.
Wow. So there's a whole universe of polymers out there,
Right.
each with its own properties and applications.
Exactly. And to understand this universe even better, we need to take a closer look at something called polymer architecture.
Polymer architecture. Now you've got my attention. What is that all about?
So this refers to how the polymer chains are arranged in three-dimensional space. We can think of them in terms of linear, branched, and cross-linked structures.
Okay, give me a visual. I'm a visual learner.
Okay, so imagine a linear polymer, like a long, straight piece of spaghetti. Simple, unbranched. Then we have branched polymers, which are more like a tree, with a main trunk and lots of branches.
Okay.
And finally, we have cross-linked polymers, which are like a net or a mesh, with the chains all interconnected.
So it's not just about the chains themselves.
Right.
It's how they're connected to each other as well.
Exactly.
That makes sense.
And the way these chains are arranged has a huge impact on the polymer's properties.
This is all starting to click for me now, but I got to ask, with so many different possibilities, how do scientists even begin to choose the right polymer for a certain application? It seems like a really overwhelming task.
Oh, it definitely is an overwhelming task. But that's where like a deep understanding of polymer science comes in handy. Scientists consider factors like the desired strength or flexibility, heat resistance, even optical properties to narrow down the options.
So it's like having this massive toolbox, right, filled with all these different polymers, each one with its own special ability. And it's the scientist's job to figure out which tool is the best one for the task at hand.
That is a great way to put it. And this is where things get really exciting because by understanding the relationship between polymer architecture and its properties, scientists can actually design polymers for very specific uses.
Okay, so we're not just stuck with the polymers that nature provides,
Right.
or the ones we just happen to stumble upon in the lab. We can actually engineer them to behave exactly how we want them to.
Exactly. So for example, a linear polymer with its straight, unbranched chains might be perfect for creating fibers that are, strong and durable. Think of the fibers that are used in ropes or clothing.
Yeah, that makes sense. A straight chain, you would pack together really tightly, creating this strong material.
Exactly.
What about branched polymers? Those seem like they would be a bit more, well, tangled.
You're right. Branch polymers tend to be less dense and more flexible because of that more complex structure. Think about those twisty ties, that come with bread bags.
Yeah.
Those are often made from a branched polymer. Okay, I can picture that. So those branches, they create a little more space between the chains, allowing them to kind of move around a little bit more freely.
Exactly.
What about cross-linked polymers? Those sound pretty sturdy.
You're right on the money. Cross-linked polymers are known for their strength and rigidity, again, because those chains are all interconnected. Think about materials like epoxy resins or vulcanized rubber. They're both great examples of cross-linked polymers.
Okay, this is starting to click now. So by understanding how those chains are arranged
Right.
and how that affects the properties of the polymer,
Right.
scientists can really create materials for just about any purpose you can imagine.
Precisely. And it gets even more nuanced than that. I mean, within each of those architectural types, linear, branched, and cross-linked, there are countless variations that can be introduced. You can adjust the length of the chains. You can adjust the type of monomers that are used. You can even add in different chemical groups to really fine-tune the material's properties.
It's like having this set of building blocks.
Right. And being able to create an endless variety of structures,
Exactly.
each with its own unique characteristic.
I like that analogy. It really captures the essence of what makes polymer science so fascinating. And speaking of, fascinating, powerful, one of the most exciting areas of research right now is the development of biopolymers.
Biopolymers, those sound intriguing.
Yeah.
What are they all about?
So biopolymers are polymers that are derived from these renewable biological sources,
Okay.
like plants or even bacteria.
Oh, wow.
And they offer a more sustainable alternative to traditional petroleum-based polymers.
Okay.
And they really have the potential to revolutionize industries from packaging to medicine.
So instead of relying on fossil fuels to create these polymers, we can use the power of nature
Right.
to create these amazing materials.
Exactly.
That sounds incredible.
And it is incredible. And the possibilities extend far beyond just like replacing traditional plastics. Biopolymers are being explored for use in everything from biodegradable implants to drug delivery systems.
That's amazing.
Yeah.
So we really could be seeing more products made from like plant-based plastics in the future.
Absolutely. And it's not just about plastics. Biopolymers could help us create this more sustainable future in countless ways.
It really sounds like biopolymers could be a game changer
Yeah.
when it comes to, reducing our reliance on fossil fuels
Yeah.
and creating a more environmentally friendly world.
Right.
That's really exciting.
It is. They
Yeah.
certainly have that potential. And another area that's rapidly advancing is the field of nanotechnology and its intersection with polymer science.
Nanotechnology, so now we're talking about the really, really tiny.
Right,
Yeah.
exactly. Scientists are now able to manipulate materials at the nanoscale, which is incredibly small, a billionth of a meter.
Wow.
And this opens up a whole new world of possibilities for polymers.
So we're talking about polymers that are engineered at this incredibly small scale. What are the benefits of that?
By controlling the structure and properties of polymers at the nanoscale, we can create materials with enhanced strength, conductivity, and even self-healing capabilities.
Hold on, did you just say self-healing polymers? That sounds like science fiction.
It might sound futuristic, but it's becoming a reality. These materials have the ability to, repair themselves when they're damaged,
Oh, wow.
which could have huge implications for everything from airplane wings to medical implants.
Imagine a world where, cracks in your phone screen
Right.
could just repair themselves.
Yeah, exactly.
That would be incredible.
And it's not just about repairing existing materials. Nanotechnology is also enabling the creation of entirely new types of polymers with unique properties and functionalities.
So the future of polymer science is all about, pushing the boundaries
Yeah,
of what's possible, both in terms of sustainability and the development of these advanced materials.
precisely. The possibilities are truly limitless.
It is pretty amazing to think about.
It is. And, while we are making all these incredible strides in polymer science, there are also challenges that we need to address.
Okay.
For example, one issue that's been on my mind throughout this whole deep dive is the problem of plastic pollution.
That's a great point. We've been talking about all the amazing things about plastic and how versatile it is.
Right.
But, their overuse and how we dispose of them has created a pretty major environmental crisis.
Yeah, you hit on a critical point. The durability and longevity that make plastics so useful are also what make them such a persistent problem when they end up in the environment.
Yeah.
It's a classic double-edged sword scenario.
So what are some of the approaches that are being explored to tackle this plastic pollution problem? I know we talked about biopolymers earlier,
Yeah.
but are there other solutions on the horizon?
Definitely. I mean, scientists and engineers are working on multiple fronts to mitigate this issue, and biodegradable plastics are a big part of that. They're designed to break down into harmless substances over time, typically through the action of microorganisms. This reduces their persistence in the environment compared to traditional plastics, which can linger for centuries.
So biodegradable plastics are like the superheroes of the polymer world, right?
Right.
They come in, they do their job, and then poof, they're gone.
Exactly.
That sounds pretty amazing.
Mhm.
But are they really like a viable replacement for all these plastics?
That's the question. And the answer, unfortunately, is not always straightforward.
Okay.
While they're making huge strides, they don't have the same range of properties and performance characteristics as conventional plastics.
So there are some trade-offs there.
Yeah, exactly. For some applications, like single-use packaging
Right.
or disposable food containers, they can be a fantastic alternative. But for things that need to be really durable or need like very specific performance, conventional plastics might still be the better choice, at least for now.
So it sounds like finding that right balance between, what it can do
Right.
and what the impact on the environment
Exactly.
is going to be key. We need something that can do the job, but also break down safely.
Absolutely. And that's where the concept of a circular economy for plastics comes in.
I've heard that term before, but I'm not sure I fully understand it. What does that look like in practice?
So it's all about moving away from this linear model of take, make, dispose,
Yeah.
which has been the dominant approach, for way too long.
Right.
Instead, a circular economy embraces a system where plastics are designed for reuse, recycling, and ultimately biodegradation.
So it's like thinking about the entire life cycle of a plastic product, from, creation to what happens at the end of its life.
Exactly. And this involves like innovations in product design, making plastics easier to recycle. It involves improvements in recycling technologies to handle a wider range of materials,
Okay.
and the development of new markets for recycled plastics so that they can be used again and again.
That sounds like it would take a lot of effort to make all that happen.
Yeah, it definitely requires collaboration between industries, governments, and consumers.
Yeah.
But the potential benefits are enormous. I mean, a circular economy could significantly reduce plastic pollution, conserve valuable resources,
Right.
and even create new economic opportunities.
That's really encouraging to hear that there are these proactive steps
Yeah,
being taken to address this. It's not all doom and gloom. There's hope.
absolutely. Yeah. And it's so important for all of us to be informed and engaged in these efforts.
Yeah.
As consumers, we have the power to make choices that support sustainability and drive demand for these more eco-friendly products.
That's a really good point.
Yeah.
Even making small changes in our daily lives.
Can make a difference.
Absolutely. Whether it's choosing reusable bags, opting for products with minimal packaging, properly sorting your recyclables, or supporting companies that are committed to sustainability. I mean, each action contributes to, a healthier planet.
Well, I think we've come full circle in this deep dive. We started by exploring how versatile polymers are, all the amazing things they can do.
Right.
And we're ending by really thinking about the responsibility that comes with their use. It's a powerful reminder that scientific advancements should always be paired with being thoughtful about how they impact society and the environment.
Couldn't agree more. I mean, the more we understand about polymers, the better equipped we'll be to make informed decisions about their use and ensure, a sustainable future for generations to come.
This has been such an incredible journey. I'm really walking away with a newfound appreciation for these materials and a sense of hope for the future, Like, we can harness the power of polymers responsibly.
Me too. Absolutely.
And to all of you listening out there, we really encourage you to keep exploring.
Yeah.
This field is fascinating. There's so much to discover. Your curiosity and engagement are so important to shaping that sustainable future.
Yeah, for sure.
And don't forget to check out the Material Science website. We mentioned it earlier. It's packed with insights and resources that can help you on your polymer exploration journey. Until next time, stay curious, and we'll catch you on our next deep dive.